The reason for selecting this place, I will come to it. See here, this is the national highway. This picture is from the Indian remote sensing satellite, kind of a software known as Bhuvan we are trying to develop. ISRO is developing. So this is our campus, and presently we are somewhere here. This is the MST radar, some 1024 Yagi antennas just backside this building. Of course, you came through this way, this towards Tirupati, and this is towards Bangalore, something around 220 kilometers this way is the Bangalore. And as I said, too big a file. Probably you can stop. I think that. I was telling about this speciality of this location. In fact, in 1992, this was formed as a national MST radar facility. And as you can appreciate, when we have a radar of this size, we should have less radio noise because we are measuring the backscattered radio signal all the way up to the ionosphere. So this location was found suitable because they are surrounded by hills and the anthropogenic radio noise is very less. In fact, that was the middle atmospheric program time. So the middle atmospheric scientists felt that there should be a common facility here, particularly for measuring atmospheric winds and of course all the way up to the ionosphere. Then it becomes a society in 1993, and of course earlier it was funded by different agencies including DRDO, CSIR, various funding agencies. But then afterwards the regular operational of this facility is taken by Department of Space, Government of India. And once one MST radar came, then people started asking more questions. How about more data on this? That I will be slightly giving a glimpse of that. So in that process, over the years, several new instruments have been added, and it grown from a facility to a laboratory. So in 2005, it was renamed as National Atmospheric Research Laboratory, so that we can take regular students, train them. There is an academic program, etc. So as I said, this is the radar. Just backside of the building, 1024 Yagi antennas. But then we have added a variety of other instruments as well. This is, for example, the relay lidar, lower atmospheric wind profiler, sonar, GPS, balloon sonde, weather station, sonar, smaller lidars, sun photometer, distrometer, and a high performing computing system, etc. So as I said, we have put a vision for ourselves. The vision is to develop capability to predict the behavior of the atmosphere through observations and modeling. When I said atmosphere, yes, we go all the way up to the ionosphere, starting from the lower atmosphere. So how do we realize this vision? It's through these steps. Of course, we need observations. To make observations, we need instruments. So we give emphasis both to indigenizing existing technology so that the instruments are under our control, they can be well maintained and operated, and whenever necessary we also innovate some new technology. So the data goes to the observations and it goes to modeling, and of course we put our neck out and try to predict it. The main purpose of this prediction is not as an operational basis, but to see for ourselves, are we in the right track. So when the prediction goes wrong, we come back to the models and see, is there any process, can we improve the models. And in turn, we can also ask, probably we can demand better observations or better accuracy or better spatial resolution and that. So this is the kind of a do loop. And in that sense, of course, today's conference is playing a major role because, of course, the modeling is the central activity in order to get, of course, to refine the observations and then to improve our understanding of the whole atmosphere, how it behaves. So just what I will do, I will not of course cover on the modeling aspect because experts are here and that's what we are going to do for the next 5 to 6 days. But what I will tell you is about the kind of instruments we have and the kind of sample data what we are getting. So what we can do better make use of this data. So as I said, this is MST radar, stands for Mesosphere Stratosphere Troposphere Radar in Garangi. It operates at 53 megahertz with a 2.5 megawatt of power. Of course, the data goes for basic research in atmospheric science, and also regular upper wind measurements are good, can be used for weather prediction model. And also when we do rocket launching, there's something around 150 kilometers from here, the Satish Dhawan Space Center, where we launch heavier rockets, including the probe to moon. So when we do such bigger rockets, we need to know the wind velocity in the upper troposphere. So this radar is a very useful tool for getting such winds. Let me show you one example of that. You can, popularly known as the tropical easterly jet, a strong wind. It can go even all the way up to 40 meters per second. So the vehicles are made to withstand the wind speed of something of this order. If it is more than that, it could be catastrophic, or sometime we may have to even hold the launch. Or of course, these informations are fed into the rocket just half an hour prior to the launch. In fact, presently the radar is working because next week we are going to have a PSLV launch carrying the several payload of France. So we basically construct a climatology, and also, as you know, for example, last 3 days we are having a very different weather. Normally February is one of the dry months, but last 3 days we are having convective systems and clouds, and that's the vagary of nature. So it's not only that we need a climatology of data, but also we need to have a real-time data just to monitor how the atmosphere behaves. But other than this, the radar is capable of getting all the three winds, the meridional, zonal, and the vertical winds. That's the power of the radar. So the vertical wind velocity during a fair weather and during convection, typically, yes, during fair weather conditions, majority of the time, of course, the winds are very low, about 30% of the time. 20% or at least 10% of the time, the winds can go up to a few centimeters per second, vertical winds. But during convective events, this is 10 meters per second. It's extremely difficult to even believe that such a high winds can extend, but it's for a very short time, over a short time scale, but that's about the convective system of the tropical region. The winds can go high. This is in one such event like that. Now let me just to give you a feeling about the capability of the system. I take you to the very upper atmosphere, that's the ionosphere. So you know that the previous solar cycle was a long minimum period. So what we were interested in also studying the so-called ionospheric irregularities in the ionosphere. This is again crucial for radio wave communications. And as you know, when the sun is active, the probability is much higher to have irregularities. But as the sun becomes calm, yes, for example, here it goes all the way up to 600 kilometer disturbances, but this is confined to 350 kilometer. But one intriguing results what we got is that these perturbations during quiet conditions, they even extend beyond the midnight hours. This is a kind of a new observations, and also lower atmospheric perturbations at 100 kilometers is also a kind of new phenomena. So this has excited our ionospheric scientists, and they are now making small models to explain this kind of observations. Coming to mesospheric altitude, this is again, of course, I'm showing the MST radar specifically just to show you the power of the system. This is the MST radar mean vertical wind for this over our region, averaged for a long time period of 98 to 2009. Again, you can see vertical winds of the order of about 0.2 meters per second in January, and of course, you know the distance between the sun and the earth is less, and these are kind of fluctuations. And some of these results are already published in Jayaraman. Of course, this is another classical, coming slightly at a lower altitude. This is the standard picture of our atmosphere. Mesosphere something around 80 to 85 kilometers. But in fact, if you do here, the measurements over Gadang, you show that the height is typically around something around 90, 98 kilometers. Of course, some of you maybe know that in the earlier, when we talk of mesopause, there is a two mesopause layers, etc. But now the probability is majority of the time that mesopause is at higher altitudes, more or less stable, but the temperature seems to be decreasing something around 0.7 Kelvin per year. That's again a new results. And of course, now immediately the exciting, you connect it with climate change, for example, increased cooling due to increase in carbon dioxide concentration in the upper atmosphere. Okay, now the radar is blind in the stratosphere. because there is no mechanism to scatter the radio waves. So in order to fill the gaps, we need a LiDAR. We depend on the light scattering, Rayleigh scattering. So this is a Rayleigh LiDAR. So from the backscattered intensity, we calculate the number density and then in turn calculate the temperature. So this is just again a sample data just to show you that in fact with the LiDAR we cover all the stratospheric altitude. What's shown is the variation in the temperature with respect to the mean. I have a reason to show that. It is just to tell you that in about a few hours, the mesosphere can have such a large fluctuations, something around minus the amplitude of about 8 degree Kelvin within about 4 to 5 hours. So that is the kind of the dynamic in the mesospheric region, the temperature fluctuations. In fact, it poses a problem to us. The LiDAR, the technique is that it's so-called inversion algorithm. You go to the top of the altitude and make the backscattered intensity correlate with a climatological temperature and start inverting backward. But when you use a climatology or your average temperature, but such a kind of fluctuations, obviously you make a long mistake. So the iterations, the results converge something around 10 kilometer below, something around 80 kilometer or so. But we have one more system here. That's the advantage of this co-located variety of instruments. This is the mesospheric air glow. This we can study the emissions from, for example, in this case, this is O1 emission, which is the layer something around 95 to 100 kilometer. So we can actually measure the temperature and put that temperature as the seed, as to invert the LiDAR data. So the earlier, without that, of course, the convergence, takes place. So you lose data all the way. But with the actual data, with the temperature, you seed it here, you can even extend the measurement. So presently, we go all the way up to about 95 to 100 kilometers. And then, of course, this the winds, it's an important parameter. As I said, radar cannot measure winds above about 20 kilometers because there is no backscattering mechanism. So if you use the Rayleigh LiDAR in a Doppler mode, we can measure winds. So then, of course, the earlier LiDAR, when I showed, it's vertical because we want to reach as high as possible. But when you want to make measurements, you need to have an angle, slanting angle. So then that has an advantage. Now these are all some of the sample data to showing that we could extend the wind measurements beyond 20 kilometers. Again, as you know, over the tropics, another big issue is the troposphere-stratosphere exchange, and then the ozone and moisture exchange taking place over this region. So wind is an important parameter. Of course, when you do that, we can also scan the atmosphere. This is something interesting I thought I should show you. Of course, we always say that the atmosphere is stratified. This is something around 80 kilometers in the region. So now the LiDAR is scanning. So you can see that the small bubbles, the temperature is, of course, this is the tropopause, something around 17 kilometers. When you go to just below the stratopause, you can see this kind of bubbles, the temperature fluctuations at that altitude. Of course, as I said, the radar, yes, it's good at something around up to 20 kilometers, but the same MST radar have problem at a lower altitude because the radar is a powerful one. The same antenna is used as a transmitter and a receiver. So when it transmits a powerful beam, so the antenna is said to be hot for some time, few microseconds. Before that, it's ready to receive the backscattered signal. During that time, of course, radio wave travels at speed of light. So around 3 kilometers, up to 3 kilometers, you lose data in the MST radar. So this is specifically developed at NARL. This is a so-called L-band 1.28 gigahertz system, a wind profiler. With that, it's a smaller system. So we basically cover the lower altitude almost starting from something around 500 meters to something around 4 to 5 kilometers. So in that process, we have almost scanned the whole atmosphere. Of course, we had two systems. One is a portable one also. And this is the Indira Gandhi Center for Atomic Research. They were interested in studying the pollution dispersal study, particularly now with the nuclear scenario, nuclear reactor in case of a unfortunate accident kind of thing, how the dispersion will take place. So, in fact, we are happy that we are helpful to them because we shifted our mobile radar and it was installed in their center and operated for about 6 months or so to get the climatology of wind over that place. In fact, that also works similar to MST radar. The transmitted beam, and we look for the Doppler shift along the line of sight and the frequency shift. So the shift gives the line of sight wind, and of course the spread, the Doppler spread gives the turbulence. The goodness of this system is that it's just 24/7, it just operates. So we can have a spectrum, you can have wind at each point, the actual direction and the speed. Of course, they are calibrated with a simultaneous GPS balloon sounding. They are good, accurate enough to something around 0.3 meter per second kind of accuracy. So this is, you can even see the boundary layer evaluation of the atmosphere during, this is one 24-hour cycle. You can see during daytime how the turbulence increases. Of course, they are good when there is a precipitation event. We can even get signal all the way up to 10 kilometers, the so-called radar bright band, the ice crystal, and the actual rain also we can monitor with this radar. These are all the other, some indigenization I was mentioning. This is the small lidar, it's known as planetary boundary layer lidar, again developed at our place. And then what we did, we had handshake with a commercial organization, so that this is the prototype. Now this is an industrially produced one, so that university people can buy. And in fact, now few systems, the company is making good profit, I heard, and already they have sold something around 15 to 20 pieces. The advantage of such a system is that, yes, we can, with the LiDAR, we can, similar to the radar. Of course, radars are a little expensive compared to this LiDAR. This will cost much lesser, almost 10 times cheaper. So, you know, the boundary layer evaluation you can see. This I am just showing because when measurements are made at the surface level, for example, ozone, this is the black carbon. It's becoming a hot issue now. Suppose if you are making it at the surface level, we can, you know, normally you end up with this kind of hump. This is during noon time. Noon time it will look as though the concentration is less. It's nothing but the boundary layer is getting higher, so the dilution of the atmosphere. So at the measurement point, these measurements are like the air what we breathe. So it looks diluted because of course it's diluted because the boundary layer has gone up. The advantage, of course, this LiDAR system, you can operate it, and this is the NDAG system, 1064, and with a double and triple harmonic, we can generate the other two wavelengths. So basically, you are looking at the atmosphere at 3 different wavelengths. The scattering, the dependence on wavelength gives on the size distribution, and also you can study the polarization, cross and vertical polarization, that can also give the kind of shape of the scatterers, whether they are ice crystals or spherical particles. Of course, we can go to cirrus cloud, again an important issue over the tropics. This is the nighttime cirrus clouds, and again with the dual polarization capability, we can even see this ratio actually gives their ice crystal to water conversion. Again, there is an important one as far as both directly and indirectly. Nighttime, of course, cirrus clouds can act as a greenhouse gas for trapping the terrestrial radiation leaving to space, and also this kind of direct release of latent heat when they are converted from water to ice or vice versa. Yeah, variety of such things. These are again sample data. You can see this is the lower atmosphere, something around 0 to 2 kilometers, cirrus cloud hanging there. Sometimes we do see something cirrus cloud thickness of about 2 kilometers. This is again a recent addition, as you know, water vapor. It's a Raman LiDAR. We could do that. But of course, now it's limited to kind of nighttime measurements, only this one sample profile at nighttime, because Raman scattering is very weak compared to the Rayleigh scattering. So daytime, the noise due to Rayleigh scattering is very large, so we are still limiting. But of course, with the Fabry-Perot and all, we can improve it. But present capability is, yes, nighttime profile we can get, and we are working on it to improve it into a continuous 24-hour Raman LiDAR. Our whole idea is that once we have this kind of system, we can have a kind of a network. We call it a Sailing Indian LiDAR network. Already something around 8 to 10 are realized. The process is going on. Of course, these are all our island stations, Port Blair and Maldives. So idea is ultimately can we get the 3D maps of aerosols and clouds over this region. Coming to, we also have this balloon program, that is the GPS meteorology balloon. And this we started sometime from 2006 onwards. Now regularly we launch at 12 university time or evening 5:30 local time. And of course, normally we do 1, but on special campaigns we can do 2, 3, and a maximum of up to 8 launches, because 1 launch lasts for about 2.5 hours. So we can go up to about 8 launches we have tried. And also occasionally, fortnightly, we also fix this ozone Sunday launch to get the ozone data. This is just a sample of the monthly variation of temperature, humidity, and UV winds, starting from 2006 to something around 212. Then this is the tropopause, the humidity picking up during monsoon seasons, and the kind of zonal and meridional winds. And again, the advantage here is, since we have co-located other instrument. This is, for example, the microwave radiometer, which can give the profile, whatever the humidity profile. So basically to intercalibrate each other, to have confidence of the kind of data we are getting, the type of errors we are talking about, because each one has its own kind of limitations, both microwave radiometer as well as the radio sonde, because it takes about 2.5 hours. And also this is a radio acoustic sounding system that you send the acoustic waves and then measure the echo of the MST radar, so you can get the temperature profile. So this is the continuous profiles are from the RAS system, whereas the thicker one are from the balloon. So this kind of comparisons we often do to make, particularly during the campaign period. This is just to give you an illustration of the ozone profile, how it looks like over our region. Of course, as you know, tropics, the ozone layer is at slightly higher kilometer, around 27 kilometers, though the ozone layer is thinner over the tropics. And of course, so the large fluctuations you see here is again anthropogenic, NOx kind of thing. So the tropopause. This is what we are interested in. This is the humidity. You can see the will vary. Sometimes it is reaching even the convective events that can touch the tropopause up to 70 kilometers. We have also have an observatory called the so-called Indian Climate Observatory Network. That's the idea is to have a network. This is the first one, where we continuously monitor a variety of gases. Something around 20 different atmospheric parameters are measured, which are of climatological significance. Here one sample is shown. This is the ozone, typical ozone variation over this region. When the institute was established as a facility in 93 to 96 period, where scientists from the Physical Research Laboratory have put their ozone monitor here. So the red dots are the ozone measured during that period. Now something around almost 1.5 to 2 decades. Now we continuously monitor it, and a kind of good news is that ozone is more or less the same, except for changes in during winter time, which are all significant to atmospheric chemistry. But nevertheless, there is not a big trend, because normally the lower surface ozone shows again a kind of marker for the anthropogenic activities. But as you have seen, this is typically a rural region and still not affected by the kind of anthropogenic activities. This is another example of black carbon measurements. Of course, this is some 4 years of data. These oscillations, this peak is during the January-February time, because again the boundary layer is shallow, so it's an amplification effect. But if you take the average, again not much trend is seen. So that's typical of this rural environment. Now I come to the most important thing which is now happening, that's a mecotropy. It's a ISRO, CANAS, our French colleagues, it's a joint project. Of course, Professor Rodam Nasma is here. He is from the Indian side, the coordinator. And of course, it has instruments like Saphir, Scarab, and Madras. Basically, this is to see the hydrological cycle. And of course, since we have this kind of instruments, so our site is kind of a ground validation site for this satellite. It's a little more than a year now, so at least 2 instruments are completely being calibrated, measured, and the data is now available on the web. So this is how we do it here. Other than the kind of instruments you have seen, we have also developed a dense network of rain gauges, something around 50 kilometer by 50 kilometer area. They are all the rain gauges. Of course, the standard, the tipping bucket rain gauge, but only thing it's made automatic, so there is a micro switch. So each tip it makes a pulse, and it's powered by a solar cell, and it also has the GPRS technology. So it automatically sends the data for every minute to NARL in the central computer here. What is shown here, these are all the rain gauges spread over this 50 kilometer area with Gadangi at the center, in the present location. This is an example of a convective event crossing this region. For example, this is Madras, where most of you have landed. There is a Doppler radar there. This is an example of a convective event going through this grid area. So we can see that as it goes, we can really. The point I like to make is that when we make a satellite measurement and the footprint is, when you say 50 kilometer by 50 kilometer, it gives 1 point. So we average it. But actually what is happening within the point is that there could be large variations within that smaller area. So we have now data, and there is one more thing. This is the kind of ground-based system, and Of course, at Gadangi we are also monitoring the, as I said, the microwave radiometer, and also we have the wind profiler. So you can see this kind of convective events, the actual relative humidity building up, the corresponding wind directions we can monitor. That's the advantage of that. It's almost 1 full day and day. Of course, the last one is that we will be having an X-band polarimetric radar to go through the cloud. So this will be a scanning radar. Of course, we are almost ready, but still not ready, in the sense that the radar work is going on in the laboratory. In about a few months' time, the radar will be there. Here, the advantage is you can even go beyond 50 kilometers, something around the range itself 50 kilometers. So plus or minus 50, we can scan around our region. So we can advantage because of the different stages of convection. We can study from shallow to deep to decaying, and characterization of storms in terms of magnitude, lifetime size, height, vertical extent, etc. So basically we will be addressing. So there is a kind of a breakthrough happening here, as Professor Narasimha was also mentioning in the morning. The tropical meteorology and the tropical convective systems are now, with the capability of a good radar, and the kind of technology we have, good computers, we are in a position to tackle the issues like that. So it's my feeling that many scientific secrets are hidden inside the cloud, in the tropical clouds, which are waiting to be explored over the tropics. Thank you for your attention, and I can take a few questions if you like.